So as promised in one of my other load sensing and pressure compensated pump videos, we're going to look at a Rexroth system where the load sensing control and load sense pressure is actually generated electronically. I've got a gauge teed in here so we can monitor the load sense signal pressure, but you notice there's no load sense hose coming into this pump. This doesn't get an external load sense signal. There's a proportional solenoid here that's going to bleed some of the oil from the pump's own discharge to the chamber where the load sense spring is. It's still adjustable. There's an adjustment on here, and we can set a load sense differential while the system's in operation. We can check the difference between pump output and load sense, and we'll still see a differential of approximately, I think it's about 270 psi or something on this particular pump control, but that could be adjusted with the tension of the spring. But we're going to control it electronically, and I've got a little PWM output. I've got a little PWM generator here that's going to give us more or less current at that solenoid, and it's got a little dial on it. I just bought this off of eBay, but it seems to be a pretty good quality one. It's able to put a fair bit of amperage, and it's a pretty good match coincidentally to this solenoid. It seems to move this solenoid through its range of motion pretty well with a 12-volt source. I'm going to hook this flow meter up to the outlet of the pump. The reason I had the line disconnected here is we were actually checking the pressure limiting compensator. So this pump control still has a PLC on it to limit maximum pressure, and it can also be adjusted. They've kind of moved the location. You'd expect to find your PLC adjustment spool on this end of the chamber, but because they've kind of repurposed this part of the pump control to operate with the solenoid, they've had to move the PLC adjustment spring over here. But on this pump, it seems like the pressure limiting compensator is set to about a maximum pressure of about 1400 psi. I'm just going to plug in the electric motor here that drives my little 5 horsepower motor that's going to run this pump, and then we can start it up. I'm going to turn the current right up on this PWM generator because this is inversely proportional. More electric current here reduces the load sense signal pressure. So I want the load sense signal pressure to be low at startup so the swash plate stays de-stroked and I don't put a big whack of load onto this small motor when I first start it up. So I'm just going to engage this. So the electric motor's turning the pump. My load sense signal should be low as I'm expecting, and it looks to be about, not even, maybe 50 psi. So that's with full current from my little device there to the solenoid. The flow out of the pump right now seems to be about 3 and a bit gallons per minute, and then it's going to the motor. And the motor shaft's turning fairly slowly, and then the oil's returning back to the reservoir through the filter. And I've got a case drain line on here because this is an axial piston motor that requires case drain. And if I set this gauge up so we can watch it, set it up so we can see it and the flow meter, you'll be able to see that when I decrease the current to the solenoid, the pump flow actually increases. So I've got about 250 psi load sense signal there now, and I've got 6.5 gallons per minute. What I didn't do is put a pressure gauge in here so we could see the differential. I should have, but we can see the increase in flow with the swash plate angle via the puck and that flow meter. And I'll increase the load sense signal to 300, and now we're getting a little better than 7 gallons per minute. And again, I'm just decreasing the current to change the load sense pressure, and I bring it up to 350, There's 400 PSI load sense signal. And now I've got about 9 gallons per minute flowing. And my motor speed's doing pretty good now. The motor shaft's whizzing around there pretty good. Bring it up to 500. This 500 load sense signal. And again, that's just being stolen through from the pump zone outlet to the load sense port. And now I'm right up to 10 gallons per minute. I could keep going, but that's the maximum rating of this flow meter. I won't reach the full pressure. I won't reach the pressure limiting compensator setting because that motor just doesn't offer enough load. It only offers maybe 700 or 800 PSI of load or resistance to flow. So that's the maximum this pressure can get. So that's the maximum my load sense signal can be. And again, if I unplug this solenoid, because it's more current, because it's inversely proportional, if I take away the current, the pump defaults to maximum swash plate angle. And that's where I'm going to see it's not even 750 PSI is the pressure being caused by the motor. And I'm actually kind of exceeding the rating of my flow meter there. Putting a little more than 10 gallons per minute through the system. So that, in a nutshell, is how the electronic control of load sensing works. And basically what I'm recreating here is a system that's typical of cooling fans on mobile equipment. If a machine's got a piece of heavy equipment's got a hydraulically driven fan, it quite typically looks like this, where they're using an ECM to drive this solenoid and turning a fan that's cooling probably several compartments, the engine, air-to-air aftercooler cores, air conditioning condenser, transmission cooler, hydraulic cooler. Certainly on our Volvo grader, that's basically what's in the fan box where the big cooling fan is moving air. And there's a speed pickup. You can see in this Rexroth motor, there's a speed pickup going in there. The barrel of the piston motor has teeth on it, creates a frequency signal. That would then go back to the ECM to tell the ECM whether the desired speed has been obtained, and that closes the loop electronically. And then if the ECM is not happy with the speed, of course it can then make more further adjustments to the solenoid to get the desired speed. Of course, it can only adjust things so far, and that's where we'd have to do a physical test to make sure our pressure differential between pump outlet and load sense is correct. And I could still use a pressure differential gauge between these two values and see if my load sense differential or my margin setting is correct. If it's not, this could be adjusted and rechecked. And again, I believe the spec for this unit was around 270 PSI of differential, but I'd have to look in the manual to get the actual spec. And I'm not sure if the pressure limiting compensator setting of 1400 is correct either, but that just happened to be what this part is set to. So that's, in a nutshell, how that system works. And just while we're watching this system operate, we should just take a look at this other flow meter I've got in the case drain line. I'm just going to increase my load sense signal again. Start this pump up. So again, the pump is de-stroked now because I have very little load sense signal, and I've got some flow going out the discharge. But I've also got some flow going out the case drain to the tune of about 1 gallon per minute. So I've got a case drain line coming off here, running through a small inline flow meter and a little filter back to tank. I'm actually going to disconnect the pump discharge and block the output, keeping my current to the solenoid, keeping the pump fully de-stroked. I'll start it up and measure that case drain flow again. I realize this is upside down, but we're seeing a little better than 1 gallon per minute of case drain flow. And that kind of answers the question that people learning about load sensing hydraulics often have when the pump's fully de-stroked, we know the swash plate doesn't actually go completely to zero angle. There's some angle to it, so the pump is still producing some flow, and it always confused me when you see the pump output blocked, or even blocked by a closed center DCV. Where's the residual flow going? And this basically answers it. When the de-stroke piston in here moves to push the swash plate against the bias spring to flatten it, it eventually uncovers a hole, either in the guide or in this one in the bore, and the oil that's pushing the piston to de-stroke it will exhaust through the holes in that bore or in the guide into the pump case. So any residual flow that is being created by the pump when it's at the de-stroke position, realizing it's not putting out no oil, it's still pumping some. In fact, this one's pumping a little better than 1 gallon a minute at this RPM, and that's all going out the case drain line. So these pumps, when they run at low pressure standby, if you've got a closed center DCV and you're not doing any hydraulic functions, you will actually feel this case drain line begin to get a little bit warm, and the housing of the pump will get a little bit warm because all the oil being pumped is dumping into the pump case and flowing out the case drain line. So that's, again, just an overview of that system. Hope it helps.